Hello everyone and welcome back. In today's video, we are diving into one of the most impactful yet often underappreciated features introduced in C++20, constraint algorithms. If you've ever found yourself writing boilerplate code to make sure your algorithms only work with specific types, or if you've had a hard to diagnose error deep in template code, then constrained algorithms are something you will really appreciate. Today we will explore what they are, why they matter, and how to use them effectively in modern C++. So what exactly are constrained algorithms? Let's start with the basics. Before C++20, most STL algorithms were implemented using function templates. These templates were extremely flexible, but that flexibility came at a cost. For example, if you accidentally try to pass a non-iterable object to stud sort, you might get a compiler error, but not at the point of the call. Instead, you'd get a long, cryptic template error deep inside the STL headers. Not ideal. With C++20, constrained algorithms are now part of the standard. These are algorithms with constraints. That is, they are explicitly restricted to work with certain kinds of input types, using C++20's new concepts feature. Let's think step by step. Before C++20, you could write something like this. That works great, but if you accidentally wrote this, the compiler wouldn't immediately tell you that X isn't an iterator or even a container. Instead, you'd get a long and unhelpful error message about template instantiation. What constrained algorithms do is bring immediate, readable compile time feedback. In C++20, standard algorithms now have constrained versions that use concepts like stud sortable, stud ranges, random access range, and more. Before we get deeper, we need to quickly explain concepts. Concepts are like type traits on steroids. They let you specify requirements for template parameters in a readable and enforceable way. Here is a simple concept. You can now write a template that only accepts incrementable types. If you try to call this with a type that doesn't support the ++ operator, the compiler tells you right away, and the error is actually readable. Concepts like this are exactly what constrained algorithms use behind the scenes. Now, let's look at the constrained algorithms in action. In C++20, algorithms were moved into a new namespace. Stud ranges. So you now have two flavors of most algorithms. The classic STL version from stud, the new constrained range-aware version from stud ranges. Here is a classic sort again. And here is the constrained version. Notice the difference? You no longer need to pass iterators explicitly. The constrained algorithm understands that a vector is a random access range, and it uses the right overload internally. If you try to pass in something that's not sortable or doesn't meet the concept requirements, you get a clean and immediate compiler error. But why is this a big deal? Let's explore the advantages. First, better diagnostics. Using stud ranges sort with a bad type gives you a clear message that's much better than 50 lines of internal template noise. Second, it's safer and cleaner code. You don't have to manually pass iterators in many cases. Instead of worrying about the iterator, you just pass the container directly. Third, unified interface with ranges. C++20's ranges are more composable and expressive. Constrained algorithms fit perfectly into the ranges world, letting you chain operations more easily. Let's look at some examples and break them down, step by step. The first example is filtering and copying. Suppose we want to copy only even numbers from one vector to another. Using classic STL, we can write it like this. With constrained algorithms and ranges, we can do it like this. Cleaner, right? And if you pass a non-range, the compiler helps you immediately. Let's take a look how constrained algorithms are declared under the hood. Here is a simplified version of how stud ranges sort might be declared. This signature does a few things. Ensures that R is a random access range. Requires that its iterator is sortable with the given comparator and projection. provides defaults for comparator and projection. You get strong guarantees before the algorithm even runs. Constrained algorithms often support an additional argument called a projection. This allows you to sort or search based on member of the object, without writing full comparator lambdas, for example in this code. The third argument, person age, is the projection. It tells the algorithm to compare using the age field. This feature makes code much more expressive and removes boilerplate. And when should you use constrained algorithms? If you are using C++20 or later, and especially if you are working with ranges, you should prefer the constrained versions. If you care about readable, compile time errors, they are a clear win. If you are working with custom types or generic code, constrained algorithms provide safety and clarity. That said, constrained algorithms do have some learning curve. The concepts behind the constraints can be intimidating at first, but they pay off quickly. Let's recap. Constrained algorithms in C++20 live in the std_ranges namespace. They make use of concepts to enforce correct usage at compile time. They simplify syntax by working directly with ranges and containers. They provide clear, readable error messages, making them easier to debug. They integrate naturally with other C++20 features, like projections and views. So while they might seem like just a small tweak at first glance, constrained algorithms represent a big step forward for safety, clarity, and expressiveness in modern C++. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.